I will overview the course and answer questions. First of all, I will mention about the subject in the course, and then I will answer questions about subjects, and then, for instance, exam, some grading policies, homework collection, archived files, all those things. In number theory, we study about principles of numbers. You may think number theory doesn't look very bad because it doesn't involve any calculus stuff, but it is not the case. We are not covering addition or subtraction. We also use addition or subtraction, but the goal is not adding, subtracting, or multiplying numbers. No. We are finding principles behind these kind of things. And then, very, very important thing is the proof. So, about 4 years ago, someone who took many courses in science and engineering mentioned that this course was the toughest one among all the courses he took. He got, of course, best score and got an A, but he said this was the toughest course because it covers proofs. For instance, prove that there are infinitely many prime numbers. Assume that you learn calculus, then your consideration is bounded. For instance, if you want to integrate a function, then there are, for instance, 10 different rules. By knowing 10 different rules, you can solve the problem. But for proofs, there are essentially infinitely many directions. In other words, you should know how to prove it. Unless you study and know, it's almost impossible to do it. In calculus, you study 10 techniques, then you can cover it. But here, it's not just 10. Another aspect is very, very important properties of numbers. For instance, there are some integers satisfying this property, and the numbers satisfying this kind of property is called Pythagorean triples. So there are certain set of numbers that we want to study. Then people may wonder why people study these things. First of all, this proof is very, very important thing in developing a lot of things. And assume that we want to develop some kind of high-tech device, then either use trial and error method or use proofs. Once something is proved, we don't have to create checking steps. That means we can make the circuit design very easy or simple. So proofs are very, very important. Another thing is, importance of proof is this one. Assume that someone mentions that there is no number, no non-trivial set of integers satisfying this. Then some of you may use computer to check these things. So you may check numbers from 0 through, 0 is trivial, so 0 is excluded. Then, for instance, you may use 1 through 1 million and check these things. And then you say, this is, I will write the statement completely and then mention it one more time. There are no non-trivial integers satisfying this star. So assume that this is the statement that you want to verify. There are two ways, either proving or using trial and error. But I will show you why trial and error has limitation. If we prove it, then this becomes a fact. Then you don't have to worry about any checking design, checking circuit, right? Or using this idea. But if it's a trial and error, then you may try this from 1 through 1 million and then find that there are no numbers satisfying these things. Then will this be enough? What about 1 million through 1 billion? Or 1 billion through 1 trillion? That means we cannot rely on this kind of thing. In other words, in some sense, this is useless. Even though it's true, it's useless if we don't prove. Do you get the point? So here, proof is everything. We are not interested in adding things or subtracting things. We are interested in proving things such as these things. Of course, this is a very famous problem. In general, we can change this to any integer n greater than 2. Any integer n greater than 2. And still, this is true. And for 400 years, people couldn't prove. But about 10 years ago, this was proved. So for 400 years, people tried to prove this thing. And at last, about 10 years ago, someone proved this thing. So there are some easy cases, and there are some hard cases like this. And once these things are proved, people use these things in, for instance, operating research, OR, or encryption. For instance, you use cell phones. In cell phones, we use numbers. Then using numbers, we send message. And if someone intercepts, mostly they cannot decode because we encrypt those messages using number theory proved by mathematicians. So this is a challenge that some company posted until last year. The challenge was this one. They gave some number, some big number, which is A multiplied by B. And if you find these things, you get, for instance, $250,000 and so on. So they posted about 10 problems, and two easy problems were solved, but other problems weren't solved, and then they closed the site. So essentially, it's extremely difficult to find the numbers satisfying these things. And if you are interested in these things, I will show you. But in any case, in number theory, we developed many, many nice theorems that we can apply in high-tech devices. For instance, you may know about RFID, radio frequency ID, and even some books have RFID. Do you have any RFID? RFID has, I cannot sketch well, but some small, like some small thing that you may see, right? So these kind of things are inside your book or someplace. Then these kind of things hold big numbers in it. So once some scanner send some electromagnetic force to this place, then it's like reflecting. It reflects, and then it sends back the number. That kind of number is read, and then it checks against the database. In other words, this was initially purchased by someone, and so on. So everything is here. Of course, it doesn't have energy or power itself, but it reflects. So one scanner sends, then it reflects, and sends a big number. So number is everywhere, even though you may or may not aware of. In any case, in this course, we will study about theories which is used in high-tech devices. So almost all cell phones use number theory in it. And web pages use number theory. For instance, you may use like, how many bits people use now? For instance, if you use 2 kilobit encryption, it's very, very difficult to decode. If you see movies, some hacker comes and then decode. But those hackers couldn't decode even 1 kilobit A multiplied by B. So total bits here was 1 kilobit, and they posted it over 3 years, but no hackers couldn't hack this thing. Just finding 2 numbers, A and B, they couldn't hack it. So very, very difficult to hack, and this is the reason why number theory is studied in many, many areas. And another thing is this thing. Assume that you make a device and you want to communicate. So device is behind the turtle. Yesterday, I watched ABC News and I found some kind of device on top of turtle back. And the device tracks down the position of turtle. Then they send signals, right? Mostly something like this. Then once it is sent, sometimes there is noise or some kind of disruption, right? Some kind of problems. Then by handling this kind of missing part, we can recover the original message. In other words, using number theory, people really recover the original message that is sent, but corrupted while it was being cut. So things like this, right? So these are all from number theory. So there are very, very many applications, but unfortunately, we don't have enough time to cover applications. If you're interested in applications, you may check some PhD courses in electrical engineering. Some design courses use these kind of things. But we want to cover very, very basic theories, but basic doesn't mean easy. And we will cover theorems that almost all the mathematicians should know, all the teachers and mathematicians. In addition to mathematicians, some engineers who are interested in high-tech devices should know. So roughly, I overviewed things. And after answering questions about grading policies or exams and so on, I will overview section by section. That way, you see what you need to study in this course. So please ask questions about exams or quizzes or stuff. Yes?
The homework that you've outlined, is there due dates on that?
Each time I have enough materials covered, then I will write down the submission date. I will post it on the web, or I will give, in both ways, right? I will mention it in class, and I will post it on the web, then you can submit.
All right.
Yes?
And when you talk about like the second exam overriding the first and the final exam being your grade, that's assuming that it's only when it's like better, right? If you do worse, that won't.
That's right. I don't want to. Yeah, that's right. In other words, I will let you know about that situation. That one should be mentioned very clearly. Sometimes people desperately need to pass this course to graduate. First exam score is bad. So bad that no matter what, the student may not graduate. So to avoid that kind of problem, I give an option. In other words, if you have nice score in second exam, then that exam can override. But even the second exam could be bad. Then the option is just using the final. But it is not easy. Usually, I have never seen anybody who get better score on the final, but at least we have an option, better than none. For instance, if you get like 30-30 on 2 exams, no matter what you get, you may fail the course. In other words, it's impossible to graduate. I don't like it. I have met a lot of students asking about some kind of excuse or something, but it is unfair to students who didn't ask, right? Some students didn't ask at all. It is unfair. So it's fair game to everybody. In other words, if you have some difficulties during the semester, but if you want to really pass, then pass by studying, not by asking me. I don't have any authority to change the grade, but I can give you the grade when you perform on the final or on the second exam or first exam. But there is a bad example. After announcing this thing, some student said, some student felt, oh, I don't have to attend anything. Just on the final exam day, I appear and then I will pass the course. But it never happened. It never happened. That's the reason why I added conditions. In other words, if you submit enough homework problems, because submitting homework isn't very difficult. So if you submit enough homework problems, then you have the opportunity. If you don't even submit, even if you get like perfect score on the final exam, I will average it. In other words, you get your first exam is 0, second exam is 0, third exam is 100. That means 33%, no matter what. Because you didn't submit any homework, I don't have any reason to pass you. That's the. In fact, I didn't even want to reveal these things until about a week ago. But I wanted to seal these facts in an envelope, in 2 envelopes, and then announce after each exam, because someone may try to take advantage of this situation wrongfully. In other words, it may ruin their success instead of helping them. But in any case, I found that it's better to announce it in the first place instead of changing the game in the course. Well, you may feel I changed the game if I announce it after opening an envelope and so on. So in any case, there is an option, but try not to rely on these options. Because I used this thing for, sometimes I didn't use it, but mostly 5 years. But I have never seen a single case having better score on the final exam than average. So try not to rely on this. Each exam is important, but somehow you have some difficulties during the semester, and you want to really pass, then pass by studying. So if you have other questions, or this question or other questions, ask me. Hi, come in, please. So if you don't have a question, I will begin to show you the things that we will cover in the course. So I will use the backside of this syllabus, subject area. What subjects will be covered will be mentioned from now on. So subject by subject, and you will see what you need to focus on. First thing is induction. Assume that you are asked to prove this thing. Then how can I prove it? How can I prove it? Then you need to use induction. So we are not, so as I mentioned before, we are not interested in this kind of thing in this course. We know 1 + 1 is 2. We are not interested in this kind of thing. In other words, we know n + 1 squared is n squared plus 2n + 1. Do you know what I mean? It's huge difference. One, do this, elementary school student can do this. Maybe one first grader can do this thing, right? But we are not interested in just using this. We are interested in proving it. So prove that. So this is the catch, right? So you should realize this, because some student had some prejudice, thinking, "Oh, this is trivial. I could do this thing from maybe middle school." Of course, you used it without proving it. Do you get it? So without proving it, you used it. Without proving it, you used it. But now we want to prove it. So the great method to prove this type of thing is called induction. And later, I will mention about the details. But right now, because I'm overviewing, I'm letting you know the reason why we need induction. So to prove this kind of thing, we need induction. Sometimes, of course, non-systematic way is possible. But as you can see, non-systematic means case by case. Then there are too many cases to prove. So instead of focusing on non-systematic cases, we want to focus on systematic cases. So one of those systematic cases is induction and a few other things. But I will show you some non-systematic example. We first define identity of operation plus. So identity of an operation plus will be defined if, so this is the definition, if x plus this identity, say, let's use 0. So identity, say 0. Of course, you could use any character or letter or symbol to represent. Then this is called the identity, right? If you don't want to use this symbol because you regard this as 0, then you may replace this by other letters such as E or anything. Do you follow me or not? So it's possible to use this thing, but I will intentionally add one more circle to distinguish this from user 0, right? User 0, and this might have different meaning. So this is the definition, and do you have any questions about the definition? Right? So identity 00 is defined, right? Identity 00 is defined if this is satisfied. Do you follow me or not? So this is the definition. Then, question, problem. Prove that 0 is unique. So this is the task. Then, is there any systematic way? No. Just you should know this case to prove. Do you know what I mean? So in this course, we have two directions, either non-systematic direction or systematic direction, but we choose systematic direction. What about non-systematic direction? There are plenty of non-systematic cases, but we don't have enough time to cover all possible non-systematic cases. So we want to focus on systematic cases such as induction, binomial theorem, and so on. So I will show you the proof. Assume that, so this is the proof. So I will call this star, 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 right? Star, star. Assume that there is another 0. So this time I will use this thing, right? Which is another identity, right? Do you follow me? So I assumed this thing. So assume that there is another one satisfying the star, star, right? Satisfying this 2-star condition. Then I will begin to prove. I will add it A, and then I will say this one equals this one plus this, because star star for this. Do you get it? If you don't understand, ask. If you don't understand, ask. It's not easy, so if you don't understand, you may ask. Because of the condition for double zero, this plus this equals, because any x can come here, right? Any x plus this is 0. Then, now, I will say this, because of star star for this, right? So what is the conclusion? We assume that there is another identity, say OX, right? OX. Then this OX should be equal to double X, right? I mean double zero. So I proved it. So this is the proof. So it's not very difficult, but unless you know this problem is extremely difficult. You may spend like 3 hours of final exam time to prove just one thing. So this is the non-static systematic case. So this is the reason why the book focused on systematic approach instead of non-systematic approach. And I will continue unless you have a question. If you do not understand why this is so, you can still ask me before I close. No questions? Then the second thing is binomial theorem. Assume that you have two terms added and then some power, for instance, nth power. Then you can multiply this out, right? Or in professional word, we say we can expand. Then what happens? Then we have x multiplied n times, and then the other extreme case is y multiplied n times, and sometimes x multiplied n minus 1 times y multiplied n times, and so on, and then added, and we may have many possible cases, and we have some coefficient here, and coefficients, and so on. And then coefficients for a general term. So we may have some coefficients. And binomial theorem determines these coefficients. So what are the coefficients? N, and then n is n minus 0, so it's 0, and n 1, and then nk and nn, where nk means n multiplied by n minus 1 multiplied by all the numbers below up to 1, and then k multiplied by k minus 1 multiplied by all the numbers below up to 1, and then n minus k multiplied by all the numbers below up to 1, right? So this is the definition. It's a little bit long principle, but it's not very difficult to apply this. So this is called the binomial theorem, and I will show you an example. Assume that we have x plus y squared. X plus y squared. Then by the binomial theorem, 2, n is 2, and then 0, x to the power of n, y to the power of x to the power of 2, x to the power of 2, y to the power of 0, right? 0 is used. And then 2, 1, x to the power of 1, and then y to the power of 1, and 2, 2, x to the power of 0, y to the power of 2. Then let's calculate these numbers. By the way, if you have 0, then we can omit. So instead of writing down n minus 1 and so on, we use the notation called n factorial. So this is the definition, right? This is the definition. So we multiply all the numbers n down through 1, and it is called n factorial. And we also define 0 factorial equal to 1. It's the definition. All these are definitions. In other words, we don't have 0 denominator because 0 factorial is 1. Then we can rewrite this thing in better form. It is n factorial over k factorial, and then n minus k factorial. Then let's really calculate these things. 2, 0. So how do we read it? I will let you know how to read this thing. Assume that we have nk. Then how do mathematicians read these things? We read this as n choose k. So we are choosing k balls out of like n balls. For instance, we have 2 balls and we choose 0 ball. Then how many ways? Just one way. We don't choose at all. So I will write it. 2 choose 0 equals 2 factorial over 0 factorial and then 2 factorial, and it is 1. In other words, there is one way of not choosing anything, just one way. We don't choose anything, then one way. What about choosing 1 ball out of 2 balls? Then it is choosing 1 factorial and then 1 factorial, and then there are 2 ways, right? We can choose first ball or the second ball. There are 2 ways. And third is identical. 2 choose 2 is 2, 1, and then 0, and then 2, 1, right? So I will specify this thing here. 1 is multiplied here. 2, 1 is multiplied, and then 1 is multiplied. So essentially the same thing. And in general, we have this kind of property. Why? If you look at the definition, you will understand the reason. If you look at the definition, but I will go up after pausing. Take a look at the definition. The definition here is what? And choose k is this one. Then if you use replace k by n minus k, then n minus k comes here, and then n minus k, n minus k is k. So we switch this. In other words, they are the same. Do you follow me? This problem. So I will show you the proof. And choose n minus k equals n factorial over n minus k factorial, and then n minus k factorial. Do you follow me? And what is n minus k? It is plus k. So k factorial n minus k. Then essentially this becomes n factorial, and then this portion becomes k factorial, and then this portion. Then by the previous principle or definition, we have n choose k. And choose k. So this is the proof. Any questions? Then let's finish the calculation. We calculated these values. So 2 choose 1. 2 choose is 1, right? This is 1. 2 choose 1 is 2. 2 choose 2 is 1, right? We calculate this value. So I will write the result. Because of this reason, this becomes 1 times x squared plus 2 times xy plus 1 times y squared. So we omit 1 when 1 is the coefficient of a term. So we can omit 1. The same one is there, right? So we essentially have this thing that you already know of. Any questions? So using binomial theorem, we derived it. There are other cases. So let's check whether you can really do this thing on your own. So I will give you 2 minutes to handle this problem. Of course, some of you may memorize this from high school calculation, but try to derive this thing using this binomial theorem. So any questions? So we can get this thing and give me any number. We can do it, right? Of course, sometimes when the number is big, we may have more terms. But essentially, we can handle the problem, right? So there are many examples that we can apply this theorem. But let's just overview this time, and later we can learn about the details, unless you have specific questions right now. Then next section is early number theory. People who are interested in numbers like this assume that we make a triangle. So we regard this as a triangle. And then next thing is this kind of triangle, right? And the next thing is this kind of triangle. Then how many dots can you get? From this, you get 1. From this, you get 3, right? How many dots? 6. What about the next one? 10. What about the next one? 15, right? Even without the shapes, you can guess, right? So these kind of numbers are triangular numbers. So people develop theorems about these kinds of things in early number theory era. In fact, we may cover a few cases when we cover this section deeply. But unless you have a question, I will continue. The next subject is the division algorithm. Very, very, very important thing. So the division algorithm. If I describe it, you may think you know. But in many, many proofs, in many, many cases, you can use this thing to prove the case, right? In many, many problems, you can use it. Division algorithm. What is it? If you divide some number, such as A, by B, then there is a quotient and the remainder. This is it. So if you divide a number by another number, then there is a quotient and the remainder. Very simple and easy, but very important. This is required in many, many proofs. So I will write it in words and in formulas. Words. If we divide A by B, then there is a quotient and remainder. Very, very obvious thing, right? Very, very obvious thing. But this kind of obvious thing is very essential in proving something. So this form, written in formula, is here. A, right, is divided by B, right? A is divided by then quotient and the remainder, where remainder is between 0 and B. Remainder is an integer between 0 and B. 0 is included. B is not included. If B is included, then we can add bigger. We can replace by bigger quotient, right? If the remainder is already B, then we can add bigger one. What is the difficult thing? Prove this. Prove this, then it is tough. Knowing this is obvious, right? You already know. You already know these things from elementary school. Prove this is not easy. You will see it. If I ask to prove this thing on the final exam, I almost guarantee that there are at most like 70 students who cannot answer the correct thing. So it's not easy to prove. You used it, but proving is a different story. In any case, this thing will be covered in division algorithm section. But if you have a question, ask me. If you don't, then I will overview the next. Greatest common divisor. greatest common divisor. What is the greatest common divisor of 10 and 5? One integer divides this, and what is the biggest? 5, right? 5 is the greatest divisor, greatest common divisor. This is very, very important in calculating the quotient of something that I will show you later. Very, very important property. So when you want to, many encryption code use this GCD inside, and you will see it when you learn the advanced things. So it's very, very important. The next thing is Euclidean algorithm. And also this thing is used in actual calculation of encryption. When you have some kind of code, then you should decrypt. Then to do it, you should use Euclidean algorithm. And it is the repetition, a repeated application of division algorithm. And where do we use it to find the GCD? When the numbers are big. When the numbers are small, you can easily know the GCD like 5, right? But I will give you a harder problem. Can you even guess? So I will let you look at the software that all labs here have. All labs here have. All labs here have this MATLAB. And using MATLAB, you can find these kind of numbers. What are the numbers? 522 and 18. Did you guess it? So, computer uses what? Euclidean algorithm to calculate. So, if you don't use Euclidean algorithm, then it will be very tough. In some programming courses, the example doesn't use Euclidean algorithm to divide, and the speed is very slow. But if you use Euclidean algorithm, it's very fast. So I will show you GCD of anything, right? Like I'm just typing anything. After this effort, I got nothing. At least I got something. So as you can see, these numbers are big. Assume that you used the sample algorithm there, then you might get some number that you might calculate it after running from 1 through square root of some number. Then it takes a long time to. So if you don't learn number theory and program, these kind of things, your program will be extremely slow, right? Your software will be extremely slow. Why? Because to find GCD, you divide this number from 1 by using divisor 1 through square root of this number. Then there are many, many numbers in between, then it takes time, right? If you don't use number theory idea. And then you need to do these things. After doing it, you store those divisors and then check what is the biggest number? Right? Do you know what I mean? So if you use just simple idea to program things, then it will be extremely inefficient. Then what about Euclidean algorithm? So I will use it. I will use Thom number here, and believe it or not, this is the technique that you will use over and over and over again in the course. So I'm showing you one time here in overview. Later, I will thoroughly cover it. So you subtract the maximum possible portion and then find the remainder, right? You divide big number by small number, then you will find the quotient and the remainder. Do you know what I mean? So let's do it. So what will be the quotient? Quotient will be 1, right? Quotient will be 1. Then you subtract this number. Then it is what? 0, 7, 2. Do you get it? Right? So you have this number, divide by this number, then quotient is 1, and the remainder is this, right? Quotient is written here, remainder is written here. From this point on, repeat it. Repeat it. So you find the quotient, if you divide this by 270, then quotient is 1, and then remainder is, do you get it? You repeat it. You repeat it down. Please repeat it down, practice. Because this technique will evolve and solve some complicated problems in the course. So you won't regret if you master this technique. So, as I mentioned before, Euclidean algorithm is nothing but the repetition of what? Division algorithm. So as you can see, if you look at just one sample, one principle, it's not very tough. But what is tough? The accumulation. It's not horizontal accumulation, it's vertical accumulation. Suddenly, once accumulation level goes like 7 or 10, it is extremely difficult. So sometimes mathematicians stack like 10,000 principles, small principles. If you look at individual part, it's not very tough. But if you stack 10,000 pieces, it's really, really high tech. So do you get it? So where is the result? 18, right? 18 is the GCD. So I didn't use computer, but I found it. And also, computer programs use Euclidean algorithm. So give me very big number, like 1 million digit number. If you use Euclidean algorithm, you can calculate the GCD very fast, extremely fast. Using different algorithm, I don't know. So Euclidean algorithm, nothing but the repetition of division algorithm handles this thing. And it's extremely important. So I will save it, and unless you have a question about the page number, note page number 2, I will continue and then show you other sections. So instead of showing all the details, I will just overview the title and a few description, because these are important. I even wrote down the details, but for others, I can just describe it. Diophantine equation is an equation of this sort. And for instance, A, B, C are numbers, such as this one. So find integers satisfying this. This is the task. Finding integers doing this. Then you should use the previous technique to solve the problem. But previous technique should be evolved to solve the problem. Because it takes some time. I will not cover it today. But Euclidean algorithm is applied to determine x and y. So if I ask this problem on the final exam, and if you don't learn Euclidean algorithm technique, then you may waste like 1 hour, but still your answer may not be correct. Even I experienced the same thing. There was an advanced theorem called Fermat's-Little theorem. If I apply it, I need to spend about 2 minutes to solve the problem, but I completely forgot to apply that theorem. So I used my calculator to find the number. So I spent about 40 minutes to find the number failed. But I couldn't solve easier problems below, so I got very bad grade. So this kind of thing is the task that you should do on the exams and final exam. Do you even guess xy? The hint is in Euclidean algorithm, but not the form that I gave you, but the evolved form. And fundamental theorem of arithmetic is it sounds very, very big, but fundamental theorem of arithmetic is what? It is this. If you have like 10, then 10 is 5 multiplied by 2. If you have 20, then it is 5 multiplied by 2 by 2, 2 squared. This is called fundamental theorem of arithmetic. The next thing, because we don't have enough time, I'm overviewing. I will just go through titles and then stop. And some conjectures, those things will be explained. And binary and decimal representation of integers. Assume that you have only 2 numbers, 0 and 1. Then how can you represent numbers? So before going further, I will use my finger. Assume that you can recognize whether my finger is bent or not bent, just 2 things. In other words, you don't know what happened for other cases. So it's bent or not bent from far apart. Then how many numbers can I represent using my 10 fingers, using this idea? Do you get it? How many? Do you guess? Can you guess? How many? Bigger.
It's like 2 to the power.
Right. 1,000, over 1,000. I will show you briefly. So all bent, then 0. 1, right? 2, 3, 4, 5, 6, 7, 8. Do you follow me? 9, 10, 11, 12, 13, 14, 15, 16. And then I will jump 32, right? 64, and then 128, and then 256, and then 512, and then 13, right? 14, and then 15, and so on, right? And then you can feel these things. Then it is 1023. So this is the representation people use. So you can use just 0 and 1 to represent all the numbers using on and off, bent or not bent. You can represent all the numbers. Do you get it? And because we have 10 fingers, decimal system was developed. Right? We have 10 fingers. We can count up to 10. And computer uses this binary system. But if you represent everything in binary, it takes more space and it's long. So they developed another system using 16 numbers. We don't have enough numbers to cover everything. 0, 1, 2, up to 9. Then we don't have any more numbers. So people decide to use alphabet as numbers. This is 11. 0 up to 9, and then 10. A is 10. B is 11. 12, 13, 14, 15. In other words, F means 15, right? F means 15. Do you follow me? 1, 0 means 16. 1, 1 means 17. So we can develop these kind of things. Of course, when you really go into that section, I will mention about the details. But unless you have a question, I will cover the next part to overview. Assume that this is a situation. You have a big pie. If you break up for 3 people, you have like 1 part remaining. If you break up for 7 people, 3 parts remain. If you break up for 10 people, 5 parts remaining. Then what is the number? Smallest possible number satisfying that kind of thing. Do you follow me or not? So you have, for instance, like about 500 pages, right? So you break up these things evenly to 10 students, or 5 students, or 11 students. Then each time, there should be some remainder. So you reverse the problem. Assume that we break up by 7, then remainder is 3. If we break up by like 11, then the remainder is 10. If you break up by 17, the remainder is 3. One number satisfies this thing. What smallest possible number satisfies this thing? That kind of question. So this kind of thing is handled by some man sharing the same last name as me. Chinese remainder there. Do you get it? So can you even guess what number satisfied this thing? In the past, this kind of thing was questioned, and people spent time to find this kind of number. I will let you know how to do it. So, but this thing is advanced, right? This thing is advanced. So in real world, this kind of thing happens. In real business, how to reduce these kind of numbers, and so on. And the next thing is Fermat's-Little theorem and pseudo-prime. This is the problem that I meant. Is this. There is some condition, but I don't want to mention about condition too much. Just this thing. If you divide this kind of number by p, right? Divide this number by p, then the remainder is 1. This is the theorem roughly. And I will mention about it. So for instance, give me any number a, except 0 and 1, right? Except 0 and 1. Give me any number 2, right? 2. And then give me any prime, 13. Then if you multiply 2, 13 minus 1 time, that is 12 times, right? If you multiply 2 12 times, then the remainder, if you divide the number by 13, is 1. This is very simple. If I apply this thing, I didn't waste time, but I completely forgot this thing. The professor used 19, number 19, and then I tried to calculate and find the remainder, and then apply this thing and this thing. And I had a very hard time, and I got the wrong answer because of my mispressing. So this thing is called Fermat's-Little theorem. And Fermat's big theorem is the one that I mentioned at the beginning. It was not proved for 400 years, and 10 years ago, a professor proved it. And the generalized version of this thing is called Euler's theorem and Wilson's theorem. If you multiply numbers, then if we divide this product from 1 through by P, then the remainder will be P minus 1. Strange theorem, right? So in the course, we are interested in principles like this. And in addition to principles, we want to prove this, the two things. Advanced theorems and then principles. So the top one is advanced one used very frequently in encryption. Have you ever heard RSA coding, RSA encryption? That thing has this application, right? So this is applied in RSA heavily. And some advanced things that require some kind of notation are covered here. So roughly, these are the directions we will go. And some interesting thing that I want to mention is this one. There are many, many open questions. In other words, even after trying so hard for almost thousands of years, people still couldn't answer some basic questions. So I will introduce a few cases and then finish. First thing is this. Assume that we have a number greater than, or we have an even number greater than 5. Even integer, right? Even integer greater than 5. Then, this is conjectured. It is prime number 1 plus prime number 2. Give me any even number, 10. Then 10 is equal to 3 plus 7 or 5 plus 5, right? Both are even, both are prime. Do you get it? Give me another even number, 8. Then 8 equals 3 plus 5. 3 is prime, 5 is prime. So this is conjectured and still open. If you prove it, you will become real rock star, right? Real rock star. So very little version of this happened. Some small problem exists, and some mathematicians in India, computer science and mathematicians in India, 3 people solved it and emailed to an expert. After reading it, even without reading the final version of the paper, the person announced it to the reporter from New York Times, and immediately it is announced everywhere in the world, in mathematical community. So if you prove this thing, maybe ABC News will immediately report. Another problem is this. There are primes such as these things, 3, 5, right? Or 5, 7, or 11, 13. These kinds of primes are called twin primes. How many of these pairs exist is the question. How many of these exist is the question. So we cannot really count the exact number. So let's be rough. Are there infinitely many of this sort or not? That's the question. It's called twin prime conjecture. And then finally, many of you are motivated by money, right? I might be also. So money problem. Money problem. If you define a function, using this thing with one catch that is a little bit advanced, but not very deep. Function for all complex plane, but a few, right? Or complex plane using analytic continuation, something called a little bit technical. Then the solution means this. This equals 0. Solution means this function becomes 0 only if, right? Only if s equals 1/2 plus some number multiplied by I. And this is called the Riemann hypothesis. $1 million problem. In addition to becoming famous, you make money. So there are these kind of open questions. But in addition to open questions like this, there are thousands, right? Thousands of problems related to this. So we will cover a few basic things. And if you are interested in this direction, you can study further. And let's quit today. And if you have questions, you can approach and ask me. Next time, I will begin to cover from the first part, section 1.1.